Right, chemistry students, today we are going to learn about the ideal gas law. Previously, we have learned about the combined gas law. Combined gas law we had learned, and this is my version, is P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, the idea of this is the combined gas law works when we have a change in conditions from one condition to another condition. But what we learned when we're going kind of forming the combined gas law is that when you have two things equal to each other and they have the same format, that we then know that both of these is actually equal to a constant. So what I'm going to do is I'm going to take this out and I'm going to put a constant in here, and then that would also be equal to P2 V2 over N2 T2. Now, this is working backwards from how when we formed the laws from Boyle's law, Charles' law, and things like that. So both of these properties are equal to a constant, and when we have a double equality, we really don't even need this. So what happens in here is now we have pressure times volume over number of moles times temperature is equal to a constant. And we have decided in chemistry that we are going to call that constant R. So let's go ahead and change that K into an R. And again, we don't need this, so I'm going to get it away. And then historically, we don't like fractional equations. So what I'm going to do is I'm going to multiply both sides by N1 T1 to get N1 T1 over here, and it's going to cancel on this side. And then that's going to give us our finalized equation of PV equals NRT. So that then becomes the equation that is the ideal gas law. The ideal gas law is PV equals NRT, where in that equation, P is equal to pressure, V is equal to volume, and then N stands for number of moles, and T stands for temperature. Now, the thing about these units are important in the ideal gas law. Pressure for when we're going to use it are going to be in atmospheres. Volume for our problems are going to be in liters. Number of moles are going to be in moles, and temperature has to be in Kelvin. We are dealing with the gas laws problem. So if your units aren't in one of these, you are going to have to change it. And if we have all of these together, we are going to have a very specific value for R. R is a constant. And if you look on your periodic table, we give you a value for R on the very bottom that is 0.0821 atmosphere liters per mole Kelvin. So those are the ones that are going to work for this. So we are going to, R is for our purposes going to be 0.0821 liters atmospheres per mole Kelvin. That is the R value that we're going to work through. So we want to make sure that we have everything in the right units. If we have everything in the right units, then we can go ahead and solve the problem. So let's do a practice problem. Now, if you look on this worksheet, there's a bunch of different R values. There's 0.821, 8.31. Those are for situations where there are different values for each of these. But in this class, we're only going to deal with pressure, liters, moles, and atmospheres. So let's work through. I didn't need to erase that. First problem. I have 4.0 moles. So I'm going to write that in. Of a gas at a pressure of 5.6 atmospheres and a volume of 31 liters. And it says, oops, I crossed over. Volume of 12 liters. I crossed problems. Volume of 12 liters. So 4.00 moles, 5.60 atmospheres, 12.0 liters. What is the temperature? And because we are in atmospheres, liters, and moles, our R is going to be 0.0821 liter atmospheres per mole Kelvin. So once we've got that set up, we can look in our problem. We have PV equals nRT. In this case, we are solving for T, so I divide both sides by nR to get T by itself. So that gives me T is equal to PV over nR. If I solve for that, my pressure is 5.60 atmospheres. My volume is 12.0 liters. My number of moles is 4.00 moles. And my R is 0.0821 liter atmosphere per moles Kelvin. So I can go ahead and plug that one into my equation, or into my calculator. 5.6 times 12.0 divided by parentheses 4.00 times 0.0821 close parentheses, and I get a value of 204. Now, because this is using our gas laws, that is going to be in Kelvin. If I want to change it to Celsius, I can subtract 273. So 204 minus 273, and that gives me negative 68.4 degrees Celsius. Usually when I ask for temperatures, I do not care if it's in Kelvin or Celsius, but I do care that you do it correctly from the problems. So that is how I work through that. First of all, identify my variables. I rearrange my equation for the variable I'm looking for, and then I solve. Let's erase that. This time I'm going to leave my R in, because for our purposes, R is not going to change. Let's look at the second problem. I have an unknown quantity of gas at 1.2 atmospheres. It has a volume of 31 liters and a temperature of 87 degrees Celsius. And whenever I have degrees Celsius, I add my 273 to that to get me a Kelvin value. So 87 plus 273 is 360 Kelvin. And I always, always, always want to use the Kelvin temperature. And then how many moles of gas do I have? So again, as I'm looking through this, use my ideal gas law, PV equals nRT. In this case, I'm solving for N, so I'm going to divide both sides by RT. So that gives me N is equal to PV over RT. Plugging my values in, 1.2 atmospheres times 31 liters. All over my R is 0.0821 liter atmospheres per mole Kelvin. My temperature is 360 Kelvin, making sure that's in Kelvin, and then I can plug in my calculator. 1.2 times 31 divided by parentheses 0.0821 times 360 close parentheses, and that gives me a value of 1.26 moles. All of our problems, I look at the problem, I identify my variables. If I ever have two of any of my variables, I have to use the combined gas law. But if I only have one of every variable, then I have to use the ideal gas law. Let's work through one more. time. Problem number 3 contains 3 moles with a volume of 60 liters and a temperature of 400 Kelvin. What is the pressure? So, identified all my variables. I have a value for everything except one, so I can go to my equation. Starting with PV equals nRT. In this case, I want to solve for P, so I'm going to divide by V on each side, which cancels these, giving me P is equal to nRT all over V. I can now plug my numbers in. My N is 3.0 moles. My R, 0.0821 liter atmosphere per mole Kelvin. My T is 400 Kelvin. And my volume is 60.0 liters. Plug the values in. 3.0 times 0.0821 times 400, all divided by 60, gives me a value of 1.64 atmospheres. Because the ideal gas law with this value for R always gives us atmospheres. So again, the units as we're going to work through the ideal gas law are going to be atmospheres, liters, moles, Kelvin, and then I have the R value. So practice a few of these with the worksheet that I am going to provide. If you have any questions, email me, and we will review these next time I see you.